I'm Kalyan.
And I'm Vincent.
We're currently undergraduate students. We've been involved in PX4 since high school, on and off with some robotics clubs. And this is our talk. Let's get started. In the past years, UAV systems have continuously become more complex. The introduction of more advanced flight controllers and coprocessors, onboard computing, smart sensors, and ground control stations has led to a need to reliably communicate between a number of components in real time. So how do we do this?
So let's pull back in time and travel back to the past, to the early 2000s. So the recent development of smaller, inexpensive sensor hardware at this time was just beginning to make consumer-grade drones possible. But open source autonomous drones largely didn't exist in the way that they do today. There were only two real components to a drone system, which were the human pilot and the drone.
Breaking it down a little bit more, let's take a look at the electronic components involved. An RC transmitter that the user is holding needs to send a signal containing the throttle and the roll, pitch, and yaw commands from the sticks to a receiver on the drone. Once there, the receiver encodes the data into a PWM signal and sends it to a flight controller, which does some path planning and sends signals to electronic speed controllers to drive the motors.
So the approach of doing this is simple enough, which is to just invent your own way, of course. So whoever makes a transmitter designs their own proprietary radio protocol to transmit data to their proprietary receiver, and then the receiver has to send the data to the flight controller, usually with a digital encoding, like PWM, PPM, or S-bus. The flight controller sends throttle signals to the ESC, usually using PWM, but other technologies also existed at the time. You just skipped, okay.
Sorry. Most of you have probably seen this, but it's probably worth recapping it really quickly. This is what a PWM signal looks like. The throttle value that you want to encode is encoded in a digital signal by varying the width, or the on time, of a pulse from 1,000 to 2,000 microseconds. This creates a square wave that's usually repeated at 50 hertz, sometimes higher. And this varies from other types like duty cycle PWM, where the width is anywhere from 0 to the entire clock period. And that's used to emulate an analog signal.
So as consumer drones advance, universities and companies start to develop autonomous drone tech. An open source community around unmanned aerial vehicles develops with the introduction of open source autopilot projects like Autopilot. Autopilots start to integrate more complex navigation tasks, such as autonomous takeoff and landing, drift-free holding, and waypoint navigation. And that all means that now the drone needs more than just a simple RC radio link. It also needs a way to transmit additional information, such as its own location and attitude, to a ground station or a single board computer and receive navigation commands back. So now we need a way to effectively transmit bidirectional digital information across a radio link. And we need a standard so that autopilots, drone manufacturers, and ground stations can agree on what format to use, and hopefully we don't end up with the fragmentation we see in RC radio. So what do we want out of a good autonomous drone protocol? We want an easy way to be able to send different message types and to add new message types over time. We also want publish-subscribe behavior for sending data to one or more sources. Finally, we also want the ability to define higher-level stateful transactions that can span multiple messages to implement more complex functionality, such as mission transfer. And finally, we want compatibility with multiple transport layers, such as serial, TCP UDP, or CAN, which we'll talk about later. So those of you who might be here from ROSCON might be saying, well, ROS can do this. And others of you might ask, well, what is ROS? Right? ROS, or the Robot Operating System, is a very popular open source robotics library and publish-subscribe framework, even at the time, which was around 2009-ish. It has easily definable message types that can carry almost any kind of data, and it has good publish-subscribe behavior and the ability to define higher-level exchanges. The big problem with ROS at this time is that it's not very good at running over serial. And the support isn't really there at the time that it's introduced, and the overhead is relatively high. And because most drones communicate over serial radio links that range in the tens of kilobits per second, that rules it out. However, we will revisit this later.
So here's a quote from Dr. Meyer, the first producer of PX4 and MAVLink. Basically, all toolkits like ROS assume TCP or IP network links, but MAV networks, especially at the time, typically used UART and serial links. And because these toolkits don't scale down to this link type, there's a lot of transcoding being done, and this leads to a lot of unnecessary effort and complexity. We can understand this more easily with the OSI model. You've probably seen this before. Just a rough way of organizing the different abstractions in networking. Lower level wire protocols like serial UART generally handle the first two layers, just sending bits over the wire and some packet organization. TCP and UDP handle a little bit more. And we need a protocol that targets all the high-level content, application messages, serialization, and routing information.
So MAVLink, or the Micro Air Vehicle Link, is introduced in 2009 to address these issues. Although the first version was a bit more basic than the one we use today, it has a few core characteristics that have kept it as the de facto solution for open source drone communication. So it has low overhead. It's able to define many message types through a message ID XML generation system. It has publish subscribe capabilities, and it's able to work on multiple transport layers. It also helps that it was quickly adopted by much of the open source drone community, including Autopilot and what would eventually become PX4.
So let's check in on what our drone looks like right now. In addition to what we had before, we've added a radio modem, which is connected to a ground control station, which communicates commands and telemetry data bidirectionally over MAVLink. We might also have a Linux computer on board, usually also using UART with MAVLink for any advanced planning. With the MAVLink standard in place for communicating between autopilots and all these external systems, autonomous drones develop quickly. As we move through the mid-2010s, we start to see some new trends. High-speed 32-bit microcontroller hardware becomes the norm. MEMS sensor technology gets much better. GPS modules start to combine multiple hardware like GNSS receivers, buzzers, switches, compasses, and even eventually IMUs into a single compact unit. And you also have other sensors like airspeed sensors, optical flow, and rangefinders that are really useful for fixing aircraft and GPS-denied environments.
So of course, all these external units need to be connected to the flight controller so that the autopilot can configure parameters and also get data off them, right? So typically, MEMS sensors will use the I2C or SPI protocols depending on the speed necessary, since they're very easy to implement on hardware. GNSS units will use UART with an old maritime data format called NMEA, and a driver on the autopilot will usually take care of configuring and reading data from these quote-unquote dumb external sensors. So this setup is very simple, and it's very cost-effective to implement.
However, it doesn't always scale up. Of course, drones keep getting more complicated. Your GPS modules that I talked about earlier include a GNSS receiver, a magnetometer, and a buzzer. Aircraft flying in urban areas also probably need an optical flow sensor. You probably want redundant GPS modules, more than 4 motors, or a smart battery system. Delivery networks need payload hardware and interfacing with that. More external units means more of these wires and more load on the autopilot. Also, the signal quality of these single-ended lines like I2C and SPI drops off as cable length increases, which poses a difficulty to larger fixed-wing aircraft. If you maybe want to mount your airspeed sensor on your nose cone, but the autopilot much further back, you might be out of luck. And let's talk really quickly about those speed controllers. ESCs have microcontrollers on them because you need brushless commutation to switch the coils. However, for compatibility reasons, they still use that PWM encoding we talked about earlier. So you have a flight controller with a powerful microcontroller, taking a throttle set point, encoding it into this PWM signal, transmitting it, and then just to decode it again. This requires a dedicated line for each ESC, and there's no way for the ESC to send any health reports back. I'll take this.
So
there's another problem here, though. What if your GNSS receivers want to synchronize your clocks? Or maybe your power monitor wants to send power usage data to the smart battery? Or maybe alert the ESCs that there's a power overload? And what if you want a black box that logs all of your data without the flight controller being involved? This isn't really practical in this current situation because the flight controller is a man in the middle processing all of this data. Ideally, we would want all our external devices to be on a single bus so we can cut down on these I/O requirements. And any device on the bus should be able to communicate with any other device. We also need a lot higher bandwidth than I2C or PWM encoding would provide. Enter CAN. The Controller Area Network is a hardware transport originally designed by Bosch for use in the automotive industry. Today, it is one of the primary ways the various ECUs or electronic control units in your car communicate. For example, your steering wheel might send information to your power steering unit. CAN has a few major advantages over the simpler transports like I2C and SPI. I2C and SPI have bus masters or specific controllers, while CAN is democratic, which basically means you don't have a single unit malfunctioning and bringing down the whole network. You can have multiple nodes all wired together with only 2 signal wires, and any combination of them can publish and subscribe messages to each other. CAN allows prioritization of messages, which is very important, and it has a 2-door differential signaling. I won't get into this in too much detail, but it gives you a lot more noise immunity in the presence of interference and over longer cables.
You want me So we can see how CAN's bus design simplifies and improves peripheral communication, right? So rather than needing separate connections for each component, we can just daisy chain each unit into one central CAN bus, which allows any device on the bus to communicate with any other device using only 2 wires. And unlike I2C, the democratic nature of CAN means that peripherals like the power monitor and the smart battery can just directly communicate with each other instead of needing to go through the central master device.
You may also notice that this does create another failure mode. If the CAN bus itself got damaged, it could potentially take down multiple nodes in the chain. But we can mitigate that by adding a second redundant line that communicates the same data.
So CAN provides a good hardware transport layer that can solve a lot of the problems we have from older technologies. However, we don't have an application layer standard for how it's used. So the message content still isn't standardized, so it's still not possible for the different nodes in a UAV ecosystem to interoperate effectively. So what can we do to solve this? So in 2014, UAV-CAN is released, which provides a message level protocol similar to MAVLink for CAN. It defines a global registry of messages, which allows standardization of components. So airspeed sensors just output an airspeed message, which can be easily recognized and decoded by the flight controller. This opens up a lot of new possibilities for modularity. So a new vendor can simply just create a new sensor, and as long as it publishes the correct message, a flight controller will be able to interface with it without any new work needed to port a driver for it. Additionally, UAV CAN libraries allow multiple redundant CAN lines for more reliability.
However, there were some issues with the original UAV-CAN design. Due to some legacy decisions, many messages were oriented towards taking that dumb pulling of sensor data, which we talked about earlier, and just putting it on the CAN bus. This leads to the CAN bus being saturated with a lot of messages that aren't useful without the flight controller processing them. Also, there was tight coupling between the application and presentation layers, which leads to some issues when you're trying to configure multiple of a single sensor or reusing an existing node or message for non-standard use cases.
So around 2019, a new version of UAV-CAN called V1 was released, which fixed some of these issues and renamed the original UAV-CAN to V0. So part of the solution was to split the presentation and application layers into separate projects. So UAV-CAN would handle serialization, while Pixhawk's DS015 standard would create a new message set. These messages emphasize the use of smaller, smarter sensors instead of high-rate raw sensor data. And they also split large messages up into multiple smaller messages to be published together. UAV-CAN v1 also removed the dependency on traditional 1 megabit classic CAN, which allowed other transports like the faster CAN-FD, Ethernet, and UART serial to be used.
However, not everyone was happy about this. There are some downsides. The flexibility comes at the cost of a lot of extra configuration, and if that's done incorrectly, there's a chance that data could be corrupted as it's transmitted over the network. Also, splitting up these larger messages into smaller ones comes with extra overhead. You have to retransmit your timestamps, and you waste some padding bytes. There's a lot more nuance that I'm going into here, but the main takeaway is that UAV-CAN v1 supports more advanced use cases at the cost of added complexity and overhead. In particular, the Autopilot project was not happy with these trade-offs and felt that v0 was a better fit for their use case. There were quite a few months of discussion about this between Autopilot maintainers and us, and eventually Autopilot decided to fork v0, and they maintained it as the name DroneCAN. To prevent confusion, UAV-CAN v1 was rebranded as the Cyphal project. So today, Autopilot and PX4 both have very well-tested DroneCAN implementations because most of the code carries over from the old v0 implementations. PX4 has prototype support for Cyphal, but it hasn't been heavily tested. Autopilot doesn't currently plan on implementing Cyphal support, but we don't know what the future holds.
So where does that leave us today? So let's take a break from all that history and let's take a look. So with the support of the community, MAVLink has moved forward to become the current standard protocol for communication between drones and external systems. So MAVLink 2, which is the current version of the protocol, expanded the frame size slightly, which provided capacity for more message types, also added support for packet signatures, and added new messages and subprotocols called microservices. These microservices are used to support a variety of new use cases, such as controlling onboard cameras and gimbal stabilizers, negotiating precision landing with a smart landing pad, or transferring files between an autopilot and a ground system for example, downloading logs. Okay. The community also introduced solutions to make MAVLink easier to use. First with DroneKit SDK, which abstracts some of MAVLink's message exchanges into methods, and now with Mav SDK, which provides high-level interfaces in most languages for all major MAVLink microservices and remains the current standard high-level library for MAVLink. Other tools like MAVLink Router also spring up into existence to better manage multiple drones on the same network. MAVLink Router and similar tools allow users to split or combine MAVLink streams from or to multiple sources and destinations for easier handling.
We're in a good position now. Autonomous drones only keep getting more complex, though, and modern autonomous UAVs might have several of these components and frameworks that need to interface with each other. For instance, with a drone running PX4, the Autopilot itself has several processes, such as the estimator, control allocation, and the commander module, that all communicate with each other with PX4's own internal IPC framework called UORB. The flight controller running PX4 might also be connected to an onboard computer running ROS2, several peripherals running DroneCAN compatible firmware, and probably a ground control station over a telemetry radio.
So the modular architecture of CAN-enabled hardware, PX4 microservices, and ROS nodes enables for a lot of possibilities for customizing a flight control setup. However, despite architecturally all being very similar pub-sub frameworks, we can see there's a lot of different conversions between these different separated networks that needs to happen, which introduces a lot of complexity into injecting new capabilities into autopilots. For example, let's say we want to add a novel position estimation source which uses a machine learning network to process IMU data, right? So in our case, raw IMU data has to come in via DroneCAN, be packaged into UORB data for PX4, then that gets packaged into MAVLink and sent to the companion computer over serial, which then needs to unpack that back into ROS2 and then run it through a neural network node before re-encoding the ROS2 message into a MAVLink odometry message. Finally, that will travel back to PX4 and then be reinterpreted into UORBs to be included in the estimator. So this protocol fragmentation can lead to bugs if the transcoding of the data is done incorrectly, and also having to juggle all these different protocols and formats just leads to a lot of developer confusion. So there's also a performance penalty because we need to constantly encode and decode different wire packet structures. So how can we reduce this?
Thanks to the work of the open source drone community and recent developments in ROSland, there have been some major improvements. ROS2 uses a protocol called RTPS DDS, which is usually too heavy for microcontrollers to use to do real-time publish-subscribe behavior. To solve this issue, eProsima has developed microXRC DDS, a transport middleware that facilitates communication between a lighter-weight microcontroller and a host computer running ROS2, which means that microcontrollers can now directly publish and subscribe messages on a ROS2 network. All this means that since yesterday, with the stable release of 1.14, PX4 has been capable of publishing and receiving UART messages via microXRC DDS, which basically makes it possible for ROS2 nodes on a Linux companion computer to directly hook into the PX4 microservice architecture to add new functionality. What would this look like, though? For instance, let's say we still have the DroneCAN data coming into UART by the PixHawk. However, instead of the convoluted method we saw previously with lots of transcoding, we can directly read IMU info from UART and publish it through the microXRC interface to ROS. Then the fancy ML allocator can just directly hook into that, calculate its results, and publish that back to UART, where it's included into the EKF, the estimator for use. Ideally, this could actually be extended to CAN networks too. Imagine for a minute if any device on your CAN bus could exchange messages natively with UART and DDS, furthermore cutting down on the need for special drivers and a lot of transcoding. This would also let us split PX4 up into multiple hardware components, which could be useful in the future for redundancy and performance load balancing. MicroXRC DDS is technically capable of running over CAN, but other protocols like Cyphal are probably more tailored to this use case. And as it stands, XRC DDS still requires more resources than a traditional DroneCAN or Cyphal node. Here's a funny graphic from the Cyphal team that illustrates that point.
So while this one network approach sounds great, this does come with some caveats, right? UORB is PX4 specific because PX4's microservice architecture stands to benefit a lot from integrating with this pub-sub architecture with ROS, because your ROS2 nodes can just hook directly into that microservice system. But other autopilots like Autopilot may have a more monolithic architecture that doesn't adapt as well. So you may still need to write custom code in an Autopilot build to read those custom functions from XRC DDS.
So what will the future look like for UAVs? One important use case that has gained prevalence recently is the deployment of large swarms or networks of drones. These could be fleets, drones being operated by a single user or company that are operating in different airspaces, performing different tasks, maybe drone delivery services or search and rescue. There's also a development of swarms, where multiple drones in the same airspace are communicating together, maybe for agriculture or just drone shows. The scale of these swarms and the possibility that multiple companies are operating in the same airspace means that drones need to be able to avoid each other. Drones crashing into other drones is really bad, and crashing into aircraft flying real people is even worse. So we need to avoid that.
So as usual, there's many solutions proposed for avoidance. Right? At short ranges, aircraft can just directly talk to each other to avoid colliding with each other. Right? Manned aircraft actually already use this approach, so they use the ADS-B transponder technology to broadcast their position to each other in close range for conflict avoidance purposes. And there are actually also ADS-B transponders that exist for consumer drones that can hook into this system. And in the US, at close ranges, the remote ID protocol is also supposed to identify a drone to nearby receivers using a broadcast signal on Wi-Fi or Bluetooth, and other regions such as the EU also have similar technology. The problem with this approach is that it obviously has a limited range, and it can also break down in more congested airspace, where each vehicle has to figure out how to repath around multiple others. So in the case of more complex long-range or high-traffic systems, a better solution might be a UTM system, which there are other talks about here, which will act like an automated air traffic controller. So you might have a central UTM system that various drones all over your city will send location and trajectory info to via wireless technology like LTE. And because the UTM system has to hold all of the information, has all the info at once, it can figure out how to repath all the drones around each other more effectively. So UTM systems have actually already been deployed in some places with great success. For example, in Shenzhen, China, right, there are over 2,000 drone flights per day, actually, which are enabled by their UTM ISS system.
So why are we talking about UTM systems? Well, large-scale UTM systems may be where MAVLink starts running into limits. It has one major issue. The system ID used to identify drones on a network is 1 byte, which makes it really hard to scale this up to a lot of drones. Every node must also process each MAVLink message to see if it's a recipient, which makes it harder to scale up.
So there are several solutions to this issue, actually some of them being discussed right across there, such as having multiple segmented networks and bridging them, or even building a custom server that maintains separate connections to each vehicle. So all of these are feasible, but they do require additional infrastructure on top of MAVLink. Other protocols such as gRPC, which is used in the web industry, and MQTT, which is used in the IoT industry, might fit this use case better. And some UTM vendors such as AirMap already actually use gRPC for this communication. However, the lack of an application level standard for these protocols means that each vendor currently has to roll their own solution, which results in fragmentation. An open standard like the UTM adapter that actually Mr. Bilal proposed earlier would help solve this. So let's recap what we discussed. Right, what does a modern UAV system look like? On higher end and industrial UAVs, DroneCAN devices from manufacturers such as Holibro and ARC are starting to replace dumb sensors. However, these simpler peripherals will still provide the best cost effectiveness for hobby drones. While DroneCAN is a mature option for most consumers, Cyphal can also provide additional flexibility for novel setups, like VTOL quad planes. The seamless coupling of the ROS2 DDS infrastructure with UORB is making it easier than ever to add new functionality to a UAV without touching the Autopilot. Several other talks during this summit are actually using this to implement navigation and estimation improvements. Finally, MAVLink is still the go-to solution for communicating with external systems such as a ground control station. Serial radio modems remain the most popular physical data link type for now, but other technology like LTE is gaining popularity. MAVLink is also being used over UART and Ethernet for connecting some onboard computers still.
So what could this look like in the next 5 or 10 years? The UORB XRC DDS bridge is just going to mature, so we'll probably see more and more setups using this. One new development you might be seeing is flight controllers that combine a traditional FMEV6 Autopilot design with a Linux compute model. One example is the ARC boards and the Holibro boards you might have seen. This is where interoperability between that Autopilot and Linux running on the same hardware would really help. MAVLink is probably here to stay, at least for ground control stations, but may be superseded for many onboard use cases. Smart ARM peripherals running PX4's CAN node and Autopilot's AP peripheral, which provide DroneCAN firmware, will become cheaper and more intelligent as they mature. DroneCAN may continue to be used for many of these devices, but Cyphal is also maturing, and as the barrier to entry reduces, it might start to replace DroneCAN. Looking further into the future, we might start to see redundant and distributed avionics as PX4 runs different modules on different hardware nodes using CAN-FD or even Ethernet as a backbone. Traffic management systems like remote ID and UTM will become commonplace. Adoption deadlines are approaching in the US and other regions. We might see the use of gRPC and MQTT to handle these large networks. Or maybe there's going to be new protocols and communication methods that are invented to tackle these new use cases. But one thing's for sure, the community's commitment to open standards over the last 10 years is what has given us the seamless interoperability we have today and our advanced technology. And as we move into the next decade of advancements in autonomous aviation, it's vital that we continue to fund and emphasize these common standards that unify our ecosystem and benefit everyone in the community.
Thank you.